Okay, says we're live. I believe it.
So I'm going to go ahead and hit that recording.
Oh, I think today, day 15. This is a good one. Right. Did I have anything left from yesterday? I don't think so. Mostly. Yeah, this is unused. Is allocator. Game memory. Transient memory unused.
Flip button there. And we should be good to go. Welcome to Handmade Hero. It is a sleepy Friday morning here. The fact that I am always sick apparently now, which is a leitmotif, of course means that I never get any sleep, which is awesome. So I'm kind of a little bleary at this point, a little bleary-eyed, but I think it should not stop us from doing.
It's a morning stream. I do like his morning streams. It's a sleepy morning here as well. Actually, not that sleepy. Alright, let's go.
Doing what we need to do today, which is just some like last odds and ends and the Win32 stuff. Before we do next week, will basically be clean up and transition over into game code, is what I'm expecting. So I'm not sure exactly what we're going to do today besides the file I/O. We're going to have to kind of play it by ear. I at least need to show you a little file I/O stuff. But other than that, we're going to have to kind of decide, probably midway through the stream, exactly what we're going to do. So, welcome to Handmade Hero. We are on.
I mean, this should be good because this monkey type. There was an update on Zig 1.1.55. I don't know, the latest one for I/O stuff. What am I looking at? Standard. I think they had IO.reader. Yeah, this was the new interface. There was a mention of breaking change. File. Never done any file stuff with Zig. I think I have done it with C. It's actually really simple in C. Get a file descriptor and you can just read. Oops. What is FS? File system. Okay, makes sense. File. Chmod. Chon. STD. What? Is terminal. Okay. P-read. P-read. Oh, what is P-read? Okay, there is a writer and a reader. Guessing mostly reading, unless save in the game state somewhere. Memoizes key information file handles such as size, current seek position, error. Whether reading should be done positionally or streaming, whether old FD to FD calls. Okay, let's carry on for now. We'll come back to that one.
On day 15, it is the end of the third week of Handmade Hero coding, and we are closing in on having our complete platform-independent stuff running, where we basically have all our game code isolated in a platform-independent layer, and we've got our Win32 implementation of the platform layer, and so that...
Spoiler alert, I looked ahead. I think it's up till day 30. There's... Or maybe like there's a mix of both. I don't know. Not sure. I looked ahead on the titles.
We're all set up to do porting in the future and that sort of stuff. If you are following along, if you're one of the folks who pre-ordered the game and are following along with the source code at home, you will want to unzip day 14 source. That is what we are starting here, obviously, on day 15. So let's jump into that and talk about file I/O a little bit before I go ahead and implement it. It's actually going to be pretty basic, the thing that we're going to do, very straightforward, not a lot to talk about, but I just want to give you the sort of the high-level overview. So basically in games, file I/O typically breaks down into two distinct categories. One is loading what are essentially read-only assets from something. Basically, this is your music, your sound, your artwork, whatever happens to be. If it's 3D models and textures. If it's 2D, then the sprite bitmaps and so on. Basically, what you're talking about when you're talking about that primary I/O function is you're talking about getting stuff off of the drive and into memory where the game can use it. And you're never touching these files other than that read. So it's essentially read only. You're never writing to them. You're never putting stuff out to the disk. You're only pulling off of the disk. And by disk, this can mean a number of things. Sometimes it can mean the network, potentially. Sometimes it can mean an optical drive. But in our case, and most often nowadays, it tends to mean a hard drive of some kind or an SSD drive. So something that's the main drive of the machine or a secondary but still primary style drive. Basically something that stores all of the user's games, and it's got all the assets on there. So that's class 1. Class 2 is saving basically the state of the game. And so this is where the game actually reads and writes. Basically what's going to happen is there's the configuration for the game. So if your game allows you to run, say, in windowed and full screen mode, that would be one example of something that would need to get saved. There's stuff like if you have separate settings for how loud the sound versus the music is, things like this. So there's stuff that's the configuration of the game. And then there's stuff that's like the state of the game in progress that the player is playing. So like a saved game file, or if there's unlocks, things that they've unlocked so far, that sort of stuff. That forms sort of a secondary class, and that class is things that we're basically writing to as well as reading from. So it's stuff that the game creates along the way and then pulls from later sort of to figure out what the state was the last time the game was run. Because obviously the game runs multiple times, and there's no way to persist things across those runs if we want to without writing them to disk first and then pulling them back in. So we basically, when we're talking about game I/O, we're basically talking about two separate classes of I/O usually. One that's for reading and writing files, and one that's for just reading them. And they also tend to have different sort of criteria for success. The sort of save game things typically are relatively tiny. They can typically be loaded in a flat call that doesn't really have to be streamed or anything like this. Whereas with the read-only stuff, where you're pulling in assets, Typically, games nowadays like to stream that stuff in the background so that the user isn't sitting on loading screens any longer than they have to. You try to overlap that work as much as possible with other things to keep the game running. So basically, with the assets, you're reading a ton of data typically, gigabytes worth of data potentially, and it's not something that's instantaneous anymore. It's not something that can be ignored as a performance criteria because it's happening all the time and it's operating on a large scale. And so typically, if you really want a well-performing game, that other class, the read-only class of I/O that we're pulling in the assets, that has to be a lot more hardcore engineering in there than just the read and write. So I want you to just understand those two things separately. Now, we don't want to, at this point, try to address the specifics of these things just yet. We kind of have to crawl before we can walk here, because if I started on 2 or 3 weeks of let's design a very efficient asset streaming system with multi-threading, we would be putting the cart massively before the horse, because we haven't even gotten a game playable yet. So it'd be really premature to kind of go in and say, all right, let's focus on the asset loading system. But obviously we also can't get our game running with real sprites or anything unless we can load stuff. So basically our job today is to just put in a minimal set of file I/O functions that we can use to get the game running, so that we can get it to a point where we know exactly what we need, at least from the asset streaming system, hopefully from both the asset streaming system and the save load system. Get it to a point where we can see exactly what we need and what would be optimal API-wise. Then we can write that API and then spend a week or two implementing the actual Win32 subsystem that will properly service that in an optimal way. So that's our goal for today, basically. So thankfully, that's pretty simple. We don't have to deal with all the complexity that we would have to deal with in a real system, because we're just trying to get the basics working. So basically, what we're going to do here is I'm going to quick say roughly how file layers are used to be done, and then how they're typically done today, because how they're done today is a lot better than how they were done. So I just want to show you real quickly how that used to work. So in the old days, basically what would happen is you had something that was basically a file handle. So typically what you would do is, let's say what I wanted to do is at startup here, when we're initializing our game, I wanted to load a bitmap. And I kind of know where that bitmap is, let's say. Normally we wouldn't know where the bitmap is. We'd have some kind of asset thing that finds assets or whatever, but let's say I just know where it is. So I've got a file name here, and I know that I'm going to load something like backdrop, or you know what, let's just make it test.bmp or something. So I'm going to try and load this file. Basically what happens here is when I'm going to load the file, I would say something like file handle, file equals open file, right? And I would pass it that file name, and then it would give me back a handle to the file. And then I would then from there do things like read from the file how many bytes I wanted. Let's say I wanted to read 128 bytes from the file. I would say that, and I would give it a buffer. So I would do something like this. I would say here's a buffer of 128 bytes, right? And then I would read from that buffer, basically like this. So maybe I'll say however big the buffer is and the buffer size. And this would typically be ifed. So I would say if the read succeeded, then I can use that thing, use buffer. If it didn't, then I have an error, right? This is an error condition. We couldn't read from the file. Now, and of course at the end of this, we would also have to clean up that file handle, right? So basically, that is basically how this works. Now, there's a lot of things not to like about this. So first of all, the way that it works is, you can imagine if I was going to do this again, if I needed to read another thing out of this, right? Maybe I got to read another 128 bytes, or maybe I got some other thing in here, buffer 2, something like that. And so I'm going to read 256 bytes, assuming I read the 128 bytes. You end up with code that looks a lot like this, right? And there's definitely things you can do to minimize the degree of iffiness going on if you were to do it this way. But the thing that I want to point out here is this is basically a streaming API. So what it assumes is that we're opening the file in a method where we're going to pull things from it incrementally. and we expect the underlying file system to basically maintain sort of a location in the file. And when we ask for bits of I/O, it's pulling it from wherever that is, right? And we're pulling and pulling and pulling, and we're assuming that basically any of those pulls could fail. Like any time we do a read, it could fail, and that's not a overly cautious assumption. Because if you think about it, at any time the hard drive could fail, the file could get locked, the file could get deleted, the user could flat out pull the drive out. If it's a USB drive, they could just yank it out of the machine. So realistically, it is true that any read can just fail. That's just flat out the case. Same thing on consoles. As the DVD drive gets ejected, well, that's the last time you're going to read from that DVD until the user deigns to put it back in the drive again. So it is a realistic concern that the reads can always fail. So basically what we've got here is we've got something that is doing a bunch of work we don't care about to support that streaming thing. Basically, we are introducing a bunch of failure cases. Every read is a new failure case that we theoretically have to handle or have some strategy for handling in a more global sense, right? So that has to happen. We also have the problem of the threading safety, and we haven't talked about multi-threading at all, so I'm just going to mention this and not go into detail. You'll understand it more if you don't know about threading later on. These file handles are very stateful. They store a location where you're reading in the file, so if two different people wanted to use the same file, they need multiple of these handles because each one is writing to a different position. So basically every thread needs its own file handle to sort of talk about where in the file they thought they were reading. All sorts of things like this are bad. And then, as if that's not enough, heaping everything on there, the final thing that's awful about this is it is totally synchronous. Like this read, the code that executes after the read can't start executing because it's going to start touching this buffer. The code that's after the read can't start executing until the read has completed. And definitely it's true that the hard drive is the slowest piece of memory in your system. Even if it's an SSD drive, it is much slower than the CPU is executing, much slower than main memory. And so basically what we're talking about right here is stalling the whole program at this point where the read happens. And so especially if we're going to do two reads in a row and stuff like that, it's just awful because it means we're like waiting and then waiting again when we could have just said, hey, we need to do both these reads, queue those up, let me know when you're done with them, and then we'll process them, right? So basically there's nothing good about streaming-based file I/O for our purposes. There are perhaps circumstances where you really do need to talk about things as if they are streams, where streams make more sense, but for our purposes they make no sense whatsoever, especially because we are always going to be reading stuff that we know how big it is. Like basically we're never going to be in situations where we're reading from an 8 gigabyte stream and we just want to pull pieces off of it, which is a case where streaming might make some more sense. If we have an 8 gigabyte file, we know how it's subdivided up and we're going to jump into it and grab a whole asset at a time. We just want to do those whole asset reads and just have the operating system tell us when we're done with them. So we basically don't want anything to do with this. Even in our test layer, even for just the basic stuff that we implement now, we want to set ourselves up for success by at least starting to go, all right, let's make a file API even for the debug, for our, sort of get training wheels purposes here to get things going. Basically, even for that, we don't want to do things this way. What we would much rather do is basically just say, for our debug purposes, we're just going to always read files or chunks of files at once in a block. We're basically going to tell it where we want to read and how much we want to read, and we're going to assume that we do all of our reads like all of that read is together and succeeds or fails. So if we're loading a bitmap file, we're going to load the whole file at once, and it's just going to come back to us as one big chunk, right? And basically what we're going to do is we're going to use that for the entire time that we don't have a giant packed asset file, and then when we move to having a packed asset file of some kind, we're going to use more like a streaming system where we're going to be multi-threaded at that point, and then we'll start talking about always having basically that one file open and doing sub reads out of it. But we're never going to do the streaming thing. The streaming thing is just not going to be the case. The only time we would do anything with streaming sort of I/O will be if we write a log file to disk for debugging purposes or something. But that's it, and we're not going to do that right now anyway. So what we want to do is something that looks more like, this. Bitmap memory equals read entire file, and we pass the file name. So it looks more like that, and then free file memory, something like this, bitmap memory. And so basically what we're going to treat it as is we're going to treat it as, we're going to treat it almost like a memory allocation. We're going to say we're going to basically allocate this file in some sense, and it's just going to appear in memory. And you'll notice, I even alluded to this in the previous stream, basically this is the one thing that we're going to allow to be a round trip. Remember I was talking about round tripping and trying to minimize that. So the one thing that we're kind of going to allow to be a round trip is going to be file I/O, but mostly only for this training wheels version. Because in the real version, we're really not going to even allow round tripping in the real version in the full concept of the word round tripping. What we're actually going to do in the real version is we're going to write to a queue that will get processed asynchronously. So this is the most round tripping thing we will probably see in the entire layer, and it's only going to be, it's not ever meant to actually run on the user's machine probably. That'd be my guess. So we're never really going to ship code like this in the final version. But basically this is how we're going to do it. We're basically just going to do a thing that says, please read this entire file. Now I could do this in one of two ways. There's two totally valid ways I could decide to do this. One would be to get the size of the file first, right? And so you could imagine something like this. File size equals get file size of the file name, right? Then I would use that game memory to basically say that the bitmap memory is going to be, get memory or reserve memory, right? For the file size, and that would do this. So this would sub-allocate out of that chunk of game memory that we have. Then we would go ahead and say, okay, then read entire file into memory, and we would give it the file name, and we would give it the memory pointer, right? The bitmap memory, like this. Does that make some sense? So we'd basically say, okay, get that file size, get enough memory to hold it, and then put it in there. That is how we would write it if this were going to be a permanent API, probably, because I would want the game, I wouldn't want the operating system to be doing more memory work than it has to, probably. I wouldn't necessarily say that it has to be that way. We still, even if we were shipping it, we could let the operating system allocate it. The reasons for that is we could use file mapping or things like that, possibly in the operating system, and also it's already something that can fail. We know that a read can fail. The read can fail, so having the operating system allocate memory and read doesn't introduce a new failure point. But like I said, I do like knowing exactly how much memory the game needs, and so having files be allocated in the platform layer dynamically wouldn't feel great to me. So if we were actually doing this API for real, we might consider something like this. Since we're only doing this in a debug sense, this is basically what we're going to do. So we're just going to let it do the whole allocation, then we're going to release it later. Does that make sense? Hopefully that makes some sense. So basically, excuse me, this will return a null pointer. It'll return 0 if it couldn't read the file or couldn't allocate the memory. And if not, then we assume we got the whole read in and it worked. And then we can process it and off we go. So that's basically what we're talking about here. Hopefully that makes a fair bit of sense and isn't too complicated. So that's basically.
If I understand it correctly, we read in the entire asset file. And then only taking what we need, because we know where everything is. Makes sense. I mean, this is how I read file anyways. Mostly because I'm lazy. Find it easier to just read the whole file.
Basically all we want, and what I'm going to do here is this is a platform call. Obviously we're calling into the platform here. So I'm going to prefix it with platform. And I also want to sort of make some kind of note that this is really not for runtime use. So I'm going to call this debug. I'm just going to put a flat out debug in front of it so that we kind of know that if we were to search through the code for this, we would kind of see it light up like a Christmas tree, that this is not really supposed to be hanging out in a shipping build. There's other things we can do about that that are kind of interesting. For example, we have this handmade internal thing, and in the future what we might do is we might do something like this, where if handmade internal exists, then we define these, and if it doesn't, we don't, just to make sure that no one can actually call them. So basically, we might have something where only if this is the case do these get defined at all. Does that make sense? In fact, we could even do that now. Maybe I just will. So basically what we're talking about here is when you go to do your first shipping build, you gotta have this stuff go away, right? Just something we could do. We'll do it for now. It seems totally reasonable. So we're going to basically just say, you know what? For file IO, that's just the way it goes. Now, that goes in this. Remember, we set this up here. Basically, services that the platform layer provides to the game. We said there are going to be a couple of them. Well, here's our first one. It's a debug ability to load a file and to release that file. So basically,
I need to, excuse me. I think I want to look up how to do that in Zig. Hey, Keyboard G. This is Handmade Hero. Oh, it's an old video series from Casey. Yeah, I'm trying to build the same thing in Zig and Linux. Yeah, that's a long way of saying yeah. Conditional. Build mode. Excuse me. I'm not sure. Used in. Excuse me. Oh, I see. What is built-in? It's called built-in mode. I mean, there's also sound, right? Audio. Yeah, so when this fails, probably need to provide a fallback. Yep, don't crash program if audio fails. Excuse me. Built-in dub mode. See built-in dub mode. This used anywhere? Must be kept in sync with the compiler implementation. Stack trace, blah blah blah. Oh, maybe. What's Sig dog guide? Build modes. Oh, I should have read more of this. Actually, this could work too. But I still don't know how to get. How old is this? From last year. Alice Turner, hello. Tin. Oh, okay, there we go. I was importing the wrong. Say is debug mode. Standard built-in optimize mode. Can I just check equal to debug? Yeah, but it doesn't know. Fluffy unicorn. Said hi to you. Yeah, okay. Hey, hello again. How are you doing? How are you finding Zig? I mean, I think it's been about 10 months of doing Zig. There's good and bad. There's at times where I get a bit frustrated, but I still think that's mostly because I don't know what I'm doing. Because I'm not very good at C, so I don't really understand the low level stuff that well. But overall, I really like Zig. I see myself continue to program in it. I built a few things using Zig so far. I think previously I built a small interpreter and compiler. And then before that, built like a tiny browser. And yeah, I mean, I really like it. Quite good. Would recommend it. A lot of people think it's a lot of hassle, but I wouldn't say so. I mean, once you understand the language, it's not that bad. Yeah, I followed the compiler book by Thorsten Ball. It was it was actually quite approachable, and yeah, it was a lot of fun too. I'd recommend the compiler book. It's pretty good. If you've never, if you have no idea what you're doing, like me. Yeah, I'd recommend it. He starts with, I think you gotta start with the interpreter book, and because that's like part one, and then the compiler is like part two, because he builds on top of the interpreter. And the interpreter is a lot simpler, and I think it's a lot more approachable if you want to start there. Okay, that's the only place it's called. I'll need a compiler or interpreter for the game engine I'm building. Okay. Yeah, I mean, if you're gonna use it, I think it's even better. I mean, this is a hobby project for me too. I think the last few ones were all hobby project. Audio server. Yeah, I can get rid of. Should I call it is debug mode? But there's another problem actually. Before I even this here, then write audio. Yeah, only attempt to write if there is an audio server. But if this fails, I think it won't even build. I must admit I was a C++ dev until 2023. Wanted Zig and Rust. I ended up settling Rust, but I'm still into Zig. I'm also thinking coming from C. Jeez. Excuse me. I would probably found Zig more natural to work with. I mean, if you're coming from C, I think Zig can be a bit frustrating at times. And I've never done Rust, so because when I'm following along Handmade Hero, and at times, like I get stuck. I'll just leave that out. Yeah, sometimes. Especially while working with, I'd say, system libraries like here. I've had to switch the audio library like 2 times and the window library like 3 times. I wouldn't say it's the syntax. I don't know. A lot of people have problem with the syntax, but I really don't think it's that tedious. I think it was more when I was linking it with system libraries, because there's some issues with Zig where you can't write some. Maybe it's just my fault. I don't know. Really don't know. When I was trying to pass a pointer to a pointer to a C method, system method, it wouldn't be allowed to write because there was like permission errors or something. I don't know how to fix it. So I don't exactly understand what's causing the problem. My best guess is that Zig doesn't allow writing. Well, it doesn't allow other process to write memory, which is held by your program, was my guess. I could be wrong. But you could solve that by allocating memory with C. Yeah. But in the last project with the compiler, I would say I didn't face any of these problems. So it's only mostly system library linking. But even then, it's I can still work with system libraries. Things work, and I can get the window working, audio working, all from within Zig. So I like it. It's my final verdict. I forgot what I was doing. I think my favorite part is so far is enums and tagged unions. I do like them. I haven't used comtime much, so I don't know. Okay, what was I doing? Oh, the debug stuff. Yeah, I think I could do it at build time. Does this return anything? No. It's deprecated. Group module dot link system lib. Okay, so it's exe dot module name options. Oh, okay, there we go. Needed. What's weak? Yes, weak, meaning that if a same name symbol is provided by another compilation unit, use package config. No field member named. Link system library. Is that a typo? Removed after 0.15 is tagged. It's already 0.15, I think. It's weird. So, what's that again? Root module dot link libc equals true. Okay, still works. I do need to fix the sound. Don't want to deal with threads right now. Totally forgot what I was doing. Oh yeah, I wanted to check options. Because dynamic libraries to be linked regardless of whether they are actually dependent on it when false. Provide no compilation. No. Don't know yet. There must be a way to check if maybe not at build time. I mean, probably here. Let's see if I mistype it. Alright, anyway, it's a problem for later.
Basically, that's what we're going to do. We're going to say here's the file name, and we're going to say here is the memory to release. And again, there's a lot of other things we might be concerned with here. Excuse me. Man. All right. Basically, the things we might get concerned with is, do we need to support UTF file names, these sorts of things. This is for debugging only, so we know we're always ever ANSI, so we don't really need to think about this much. Now, I want a symmetric thing. So in addition to reading, I would also like to be able to write. So I would like to be able to say platform write entire file and write.
Oh, now I remember what I was doing. I want to define methods to be used during debug. But it's not that important right now.
Entire file would just be here's the file name to write to, here's the memory to write, and then here's the memory size, how big it actually is. Now, one thing we might do is we might want to say, or we're never going to allow writing of files that are more than 4 gigabytes, at which point we would make this a uint32. I don't know which one I want to do there. It's I think we may want to support writing giant. Maybe not. Nah, probably not. So we could just say that that's going to be under that size. So there you go. That's basically all we're talking about here. And so that's really pretty straightforward. You can see if we compile, everything compiles fine. There's not much to talk about there. All we have to do is we got our linker warning, says we haven't implemented these, but I can just go implement these now. So here's our file layer. We go into win32 handmade.cpp. We're just going to drop those in there. And you can notice we already did the implements file. I was talking about this, and I already had dropped this in here as a note. So basically, we're going to go ahead and delete that old stub and make this here. Okay, there we go. These should be marked internal as well. Let me go ahead and mark that, because basically, like I said, all of our functions are internal, just to help the compiler out so that it knows there's no external linkage. We're all compiling in just one file. So what I need to do here is straight up call Windows and say, hey, Windows, read this entire file for me. Nothing interesting going on here. It's going to be the most basic thing that there is. We're not going to get fancy at all. So we're just going to call a function called create file, and also one that gets the file size. So basically, this is what we're going to call to open that file. Basically, well, I'll talk about what that does in a second. I believe there's just a flat-out file size call that will just tell us how big a file is. Nothing particularly complicated about that. So there we go with that. And I think that's mostly all we're going to need. We're going to get that file size. Then we're going to, of course, excuse me, have to close the file as well, which is the close handle call. It can close any type of handle, including a file handle. And then we're going to need one more, which is read file. And that will be the way that we'll actually get it in. So there we go. All right. So really, there's not a lot of mystery here. I'll kind of explain what these things do, but it's like pretty darn boring. So basically what happens is first we say, all right, we've got to get a handle to a file, because operating systems like handles. Basically the way operating systems tend to work is there are resources that are on the operating system side, sockets, files, streams, whatever they are, processes, you name it. And basically they need a way of talking about those to you, the process that's running. And they use handles for that. Those are typically just indexes into a table or pointers into kernel memory that say, here is the thing that I'm talking about on your side. So for a file, we basically want to say, hey, here's something I want to read from the disk. I'm going to give you the name of it, and I want you to go open that and give me back a handle so I can keep talking about it to you and telling you what to do to it, like reading it and getting its size, right? So basically, we need to pass the file name, then we need to pass a bunch of stuff that's largely meaningless for us, but that makes some more sense in Windows if you actually care about other things. Basically, what these are like things like how we need the file to be opened, how we need it to be accessed. So if you look in here in the documentation, MSDN, you can see this desired access. Basically, we're just telling Windows what we actually need to do, because Windows may allow multiple. There's basically different ways of opening files where the operating system can determine whether multiple people can open the file at the same time. So basically, we need to tell it, do we need to read or do we need to write, or both? And then we also need to tell it later, this is what share mode is, the next parameter. What do we allow other processes to do? So we may open a file for reading, and we know that we want it to not be written to at that time. So we may say, well, another process could open it for reading, but don't allow them to write to it, right? Similarly, if we're writing to a file, we may say, don't let any other process read from it or write.
I guess this is like totally different, kind of. Read as file fs. S dot create file. Absolute W. What's that? Creates, opens, and overwrites file within file with write access based on absolute path. Okay, so there's just 3 options. Let's do it outside the main, probably at the end. The file name. That's const. Let's see, you wait. What is the file? Okay, it returns. Yeah, why not? Absolute. Is the absolute path flux. Read, truncate. POSIX is in this file, the file system mode. The file will always be created in. Sure that creates the file, otherwise causes. Whether the file will be created with read access. Maybe. With no respect to locking API, can still get access to the file despite the lock. Yeah, I'll just leave it in default mode. How would you call it? So I guess I can just leave it empty. I didn't need a method for this. Let's go the file stuff. Yeah, and what else do we need to do?
From it because we're modifying it right now. So it's basically like a mutex. It's a lock that basically says, all right, when one person has a file open, the operating system allows them to basically say, don't let other people do stuff at this time because we'll create errors by doing that. So what we know here is we're just reading a file, so we can just say generic read, right? We're just going to read from the file. And then the share mode, we know that basically anyone else could read from it, right? But we don't want them to delete or write to it because we don't want them to modify it while we're doing something, while we're doing this one read that we do. We're only going to have it locked for a very short time, so that's fine. So there you go. Now security attributes we don't care about. This is basically if we're trying to do things more about like whether the file handle can be passed to a sub-process and all. There's all sorts of other things that you might care about, but we don't care about those for our purposes. We're just reading the file ourselves. We don't have a sub-process. We don't have anything else we need to worry about there, so it doesn't matter, so we can just pass null for that. Again, I use 0 instead of null. Some people like to use null, and so if you want to use null, that would be a null for you, not a 0. Null is defined to be 0 in Windows. So when we're opening a file, obviously we also have the ability in Windows to basically say create the file or don't create the file if it didn't exist already. So basically what it kind of needs to know is if there's already a file on the drive, what should I do with it? And if there isn't a file on the drive, should I make one or should I return an error, all that sort of stuff. So this is a read. This is our read call. We're saying we're going to read something from a file. So what we want to do here is we want to say, okay, I want you to always open a file that already exists. If there isn't a file existing, I want that to be an error so that the game knows it was trying to load an asset that just plain ain't there, right? So that's it. So flags and attributes is basically stuff like, you know, when you go, I don't know, you probably have experience with this. If you're a programmer at all, I'm sure that you have. If you go onto your drive and you right-click on something and you get properties, there's this stuff down here, read-only, hidden, that sort of stuff. Basically, you could specify those things. If you were creating the file, you can specify those things. You can also specify a bunch of other flags that have to do with how the operating system is going to use this file, like weird stuff like delete on close, right? So you can have like temporary files that kind of get cleaned up immediately after you close them where you don't have to do it, and the operating system kind of can do extra stuff there because it knows. There's all sorts of other stuff. Overlapped I/O is like possibly how we'll do. I think we might use I/O completion ports, but ignore that stuff for now. There's things you can basically set that are how the file will be read from, and those might be relevant to us in the future, but they're not right now. So I don't think we actually have any flags and attributes. I can't remember. It's been a while since I've written any file I/O code in Windows. Typically, I use I have kind of stuff that I have written a long time ago and used. But I don't think there's anything we really care about in here, so I think we can be 0 again. And then the template file, again, we also don't need any of that stuff. So we're basically fine with this. And basically, let's see, not equal to invalid handle value. That is what it will return. So basically, we're just going to go ahead and try to open the file using these flags. I think I've got them set right, but we'll double check and make sure that I do. Then we'll go in here. Once we have an open file handle, we can ask for the size. Here's the file size. Now get file size is a little antiquated. So we might want to call get file size ex. Let me show you why I say that. We don't really need it for our purposes, but we could just to be a little more complete. Basically, what we've got here is, yeah, so you can kind of see what happens. This get file size function returns a D word. Basically, you it's just kind of janky. Let me see if there's a less janky one. I don't know if there is or not. Yeah. So we'll use the non-janky one. I'll tell you why it's janky, and then we'll go from there. So basically, get file size was written kind of in the days before 64-bit. A file obviously can be more than 32 bits of space wide, right? 32 bits is 4 billion bytes roughly, and that's a 4 gigabyte file. Now, anyone who's ever BitTorrented stuff knows that 4 gigabytes is not necessarily that large. You could have files that are more than 4 gigabytes large, a single file. So, when you ask for the file size, it needs to return a 64-bit value, because a 32-bit value won't hold the size of some files on a drive. There's nothing that says that files on a drive have to be limited to 4 gigs anymore. I think there used to be, in the FAT32 days or something, there's probably a limitation or something like that, or in the regular FAT days there certainly was. But there isn't anymore, certainly not on NTFS and not on ext4. So basically what you end up doing is when you do a get file size, it's got to return you 2 halves of the 64-bit value. The high 32 bits and the low 32 bits, and then we would have to basically shift them up and OR them together to put back together the actual 64-bit value, right? Which is not what we want. We'd rather just have it return a 64-bit value to us. So there's this get file size ex thing, and if we look down here, we can see it was supported on Windows XP, which is our minimum supported client. So this is a function they introduced later, which basically just flat out gives us the 64-bit value, which is what we actually would prefer. So what I'm going to do instead is use get file size ex, pass it that handle that we opened, and then pass it the address of our file size value, right? So that way we don't have to deal with that jankiness. It just makes life a little easier for us, which, you know, we want if we can get it. So we're going to define a large integer. We've seen this large integer before. I don't know if you remember when we were doing query performance counter. So that quad part is the 64-bit value that we were looking for. So basically file size.quad part is what we're looking for. Excuse me. And all we're going to do here is, assuming that we got the file size, we will go ahead and try to virtual alloc that thing, basically, and something that's that big. That will give us our memory. So this is essentially the result that we're going to return, void star result. And then we are going to see if we got it. If we got the memory, we're going to go ahead and try to read into it via read file, like so. There we go. And assuming that worked, there we go, put that in there, then we're going to have to handle some failure cases. All right. And then, of course, at the end, assuming that we were able to open the file, we're going to have to close the file as well. So we're going to go ahead and close this file handle. There we go. All right, so a couple things to talk about here, and then, of course, I'm going to return the result. There we go. Now, this will just be on here. Freeing is trivial compared to, it's just virtual free, I believe. What was the... We've never had to free memory before. This is our first time. This is our first time, people. I think it's just virtual free. I don't remember what we need to pass. The address, the size. Okay, we're releasing it though, so we don't actually need the size. So it's just release memrelease. I think that's it. So we're just going to release this memory, and that's all we're doing. So that should be it. Address free. Let's see. Address size free. So basically what's going to happen here is we have a little bit of a janky scenario going on, but there's not a lot we can do, really. We could memory map the file. You know, there's other things we could do here. I'm going to try and keep it a little simpler than that. So basically, doing it in the straightforward way where we read it like this, basically we're going to read from the file handle. We're going to pass it the buffer that we allocated, right? We're going to ask it to read the file size that we allocated as well. And there's some jankiness in there. And then let's put that in there. as well. And then we're gonna pass 0 for that overlap parameter, because that's the overlap parameter is a thing that basically lets us say, oh, we want to do this read asynchronously, and we're not at that point yet, so we're going to pass 0 for that. So we're just passing the handle, where to put the stuff you read, how much we want you to read, and then a pointer that says the result. So basically what you can see here, excuse me, is if we really wanted to support reading large files, we would have to actually do a loop here, because the read file function in Win32 doesn't actually let us pass a 64-bit value. It was a D word here, so I'm assuming I'll just get a compile error, hopefully. Oh, right, I got to do our virtual alloc. I actually have to pass the rest of the things to it. There we go. Like that. So we've got 0 and that. There we go. So basically the problem here, oops. There we go. The problem here is that this guy, this quad part, is actually a 64-bit value, but read file.
Wonder if you can read. Position lock mode p read. Okay, what is p read? File buffer offset. Redo. Okay, so it's a usize. So oh fuck, I forgot about this. Does that mean this is async? Possibly. Standard IO reader. Okay, I think it's the same thing though. Can you do something like file dot? Oh no, how do you even use? Okay. Fulfills standard IO interface. You need reader and destination. Oh, destination. Slice of UI. Read. I am guessing that reads all. I mean, it can be a const pointer. Get size. It's easier to read here. Okay, stat. File dot stat, and I think I did see it here. Kind, size, yeah. That. Do I get stat? Stat at L stat const file size is stat dot size. Comes file size. I should compile. I mean, I'm not using the methods, so was that a problem? And file size. What else can you get from stat? I think size is fine. I think it's catch error and failed. Unable to resolve comp time value. I did think that might be a problem. It's fine. I can pass allocator, allocator. Because it needs to. Wonder if I can reset just this. Because I'll run out of memory otherwise. After you read the file a few times. I'm using the arena allocator. definition is allocator dot alloc. Type and size. I need to pass allocator. Tour. Add a union is ignored. Fair point. Set again, non-void. Turn type. Think for now, I'll just make it void. How do I make it? Can I just do? Oh, okay, I don't return the file handle. Yeah, you can't. I think you have to be explicit. It's the same, I think, like Go. Oh no, I think in Go it's fine. You can ignore. Selected error union type found. I am using that wrong. Catch. There we go. Don't need try. That's why. Okay. Valid string. Yeah, it's an error. That is my bad. was in the right place. Ready for now. Reached unreachable code. Create file absolute. Oh, it's not an absolute path. What are the other options? Say create file current directory. Current working directory. There's just no, there's no create file. Why is that even used? Ah, I see. Create file. Overwrite file with write access. File the close on the result when done. Okay, that's neat. I didn't know that. Okay. Create file. Subpath. Guess I can remove this. And flags. Okay, there we go. I want to like stop playing audio for now. Okay, that is a file. Yeah, test. Empty. That wasn't too bad. Platform. Read entire file. Oh. Yep. Size 0, red 0. Read. It's all reset. The problem with using an arena allocator here is yeah, because every time we read file, it'll just create more memory. I might have to use a different allocator here. Overuse part of the transient memory. Nah, maybe not a good idea. Actually, how much space do I? I don't really use it at the moment. Got about a GB of space. But that is for the game though. Yeah, I don't know. Let me write to do. Cannot use arena here. We'll allocate memory. Out games lifecycle. To switch allocators or alright, let me continue.
Unfortunately, doesn't actually take a 64-bit value. So if we go in here and we look, it just takes a D word, right? And the problem with that...
Hang on, sorry, got distracted again. I want to check memory. Actually, not a bad idea. Yeah, standard dot debug print current memory usage. Tensor use size. And no print FPS for now. And I want to read it twice. Oh, but fuck, it's empty. That's okay. Let me just check how much space I use. That looks. Does that look right? Actually, way too much. Guessing this 1.6 GB. 1 GB here. Where's the rest of it coming from? Oh, the sound buffer. Right. And the video buffer. I think the sound buffer is quite huge. It's holding 1 second of data. 48,000 times something. That's actually not a lot. It's only about 96,000 bytes. Anywho. Okay, let me just continue for now.
That is the D word is only 32 bits. So if the file actually were larger than 4 gigabytes, this would fail. The allocation would probably succeed, but the read would just flat out fail. Now we don't actually care about reading in our debug. We're never going to read a 4 gigabyte file into memory in one go like that. That's not something we're ever going to do. So what we can do here is just assert. This is again where the assert thing comes in, which is nice. We can just assert that file size quad part is basically less than the maximum value that we would get here, right? So this sort of a thing. Basically that it's less than the maximum 32-bit value that you can have. Or up to it, I suppose we could be up to it exactly. Now, one of the nice things we could do is, and this is something maybe we'll do next week when we're sort of going through to-dos, is defines for maximum values. Because it would be nice here to be able to do something like uint32 max in that, so people know why we're trying to test against that, because we're basically saying it's the max value. And standard int.h, I believe, or limits.h, there are C runtime library function, there are platform defines that tell us these values, so we can actually get them pretty easily as well. So anyway, that's something, but for now we could just say assert that the size is less than 32 bits, and then we're fine, right? Then we're totally fine. So after that, we could do something like this: file size 32. We could even make it explicit what we're doing here, right? And off we go. So that is one way to do it. Another thing we could do that's also safe, and I kind of like this a little bit, is we could define something like this, where we do safe truncate 32 or something like this. Like that, and then we pass an int64 value, a uint64 value here, so maybe something like this, safe truncate uint64, and that basically says, all right, I've got a uint64, I want to truncate it to 32 bits, and I want to make sure that there's an assertion around it so I know. So here's the value. I'm just going to bake this, what we did, in there, right? So I'm going to assert that whatever the value is less than whatever the maximum is, right? Something like this. And then I'm going to go ahead and say, all right, the result is going to be that thing truncated, and then we return it. So just a nice little inline function here that does that truncation. Now I can see what's going on a little cleaner. I can say, all right, safe truncate that, and that makes me aware that at least always in debug mode, I know that I would get an immediate hard error if for some reason the things weren't small like I thought. So you know, I'll put that out in our platform independent layer, because it is platform independent, basically in our little utilities here, right? That's just kind of a nice thing to have. So I like that. I like doing stuff like that, where now I can just bake it out and just know, now from now on, anytime I'm going to do one of those truncations, I can feel a little more comfortable that at least they're getting asserted. So if someone starts using this code for purposes other than what I thought, they'll immediately get that assertion and know what's going on, why their code isn't working anymore. So that's one thing, right? There we go. So okay, so we're okay, because we're basically saying we're never going to read files that big, so it's fine. So we're checking the file size and make sure that it's going to work, and it will hopefully work. Once we get in here, we're going to do our read file, and our read file can fail, of course, right? So basically, since our read file can fail, one thing before I forget too, these are all A functions, right? Because they take a file name. Yeah, so this is a create file A for those of you who are doing Unicode at home. All right. Anyway, so basically when we're doing this read, the read can fail. If the read fails, we don't want to return the memory. We want to free it right here, right? We want to basically say free this memory that we had immediately, because we don't want the memory left sitting around. So that result that we did, we want to free that and set it to 0, so that it's as if we never allocated it in the first place. It's the same as an allocation failure, basically, if the read fails. Because otherwise, if the read fails, we still had the memory. We'd return the memory to the caller. They would think they read the file, but actually what they have is garbage memory there's no sense in forcing the layer to figure that out on its own, right? So we
I think when I use an arena allocator, freeze the no up as memory. Okay, there is no need to free anything manually. Can I call free? Pointer must be a single line pointer. Can I just call free? Hey, look at that. It did change. No, it didn't. That's weird. Well, I mean, to be fair, there's no... I think that's fine. That'll do. I can remove this. Question would be when to free it. Okay, I think I know what to do. I'll just pass in a buffer. Slice of view weight. And this can... I need file size. Get that. Actually, this doesn't even need to be a method. For now, you can just read it here. But then I have to handle the errors. Okay, yeah, just separate out this bit. If I'll handle... No, I'm gonna leave it as is for now. quite, I mean, it's quite trivial.
We don't want to do that. So assuming here this is the success case, file read successfully, and then we go, there we go. Now you might wonder why I left an empty one here. I like to get further nested in success and put my errors in the else cases, and you know, logging in there. So you know, maybe we'll do some logging here, right? That's the way I like things to always look. That is the only reason that that looks like that. So we could have logging in here for inability to open files and stuff like that, right? Makes sense. So that's all that is. Yeah, pretty straightforward. So that's basically it. There isn't really a lot else to it besides that. And if we were going to do a write, it's basically the exact same stuff. Let me compile this and make sure we're working here. Oh, right, the actual bytes read. Let's see here. dword bytes read. That'll tell us how many we actually read. Now the interesting thing here is technically the read could read less than how many we asked it to read. I don't think that's actually possible in any scenario that isn't gonna where the read isn't gonna fail. Meaning I don't think that it can read less if we know that the file is that big. If someone went in and truncated it, maybe in between, then it would fail. So you know what? I might go ahead and say let's handle that case as well. Let's say here, let's just also say that we want file size 32 to be equal to bytes read. So we're basically going to say do this read, assuming the read returned true, check to see whether bytes read and file size are equal. If they are, then we consider it success. Otherwise, consider it a failure. Because just in case someone truncated the file in between there and we only read part of it out, because technically the way read file always works in things is you can specify a larger value than the size of the file than is left in the file, and basically it will just give you back however much it could read. That's just how they're usually defined, and that's not an error, that's just allowed. And so if someone went in and truncated the file while in between when we got its size and when we read it, technically we would hit that error case where the read file would succeed, but we would get back less bytes. So we want to consider it a success only if we actually were able to read the whole file. So I'm just going to go ahead and say that. Now notice we took advantage of the short circuiting here. When we did the read file, we're saying we're not going to bother doing this check until after this is done. And so the fact that we know that this has to happen before this is the only reason that works. If C could do these in any order, this code wouldn't work properly because this could be evaluated before the read file, and of course read file modifies the bytes read, so that wouldn't work. But we know that C is required to execute these in the order they appear on the line. That's how the operator AND is defined to always do the thing before it first and then the thing after it. So we know that that's going to be okay. So that's our read. We can step into it now and see if it worked. Of course, we know that that file that I asked for doesn't exist. So what should happen if things are working properly here is it should be an error. So let's go ahead in there. I actually want handmade.cpp, which is not open yet, but that's okay. We'll just set a breakpoint where we actually call it, and then we'll step in there. So, all right. So we come in here, and basically we're going to call this. Again, we're passing it test.bmp. So that's going to call create file, and that should just flat out fail, and it does. So what we need to do here is we now need to give it a file that actually could be loaded, something that actually exists. So I'm just going to pick a random file temporarily for purposes of testing. Let's take a look. What is on W colons? Let's see, handmade. In fact, you know what we could do? We could just say this. That is a C preprocessor macro that inserts the name of the file that got compiled. So I could just try to load myself, basically. So I come in here. Let's see. Let's take a look at that file name. W handmade code handmade. Always good. So let's go in there and see if we can read that. We did the create file, and the file handle came back valid this time. We take a look at it. We get the file size, and let's see what that file size actually is. It is, well, you know what? Let's see it in decimal, because that would be better. There we go. So we'll take a look at that file size. It's 3091 bytes. Does that square with our expectation of what the file actually is on disk? Yep, 3091, exactly right. So that worked fine. We're going to alloc that memory. We'll take a look at it, check the results. That works fine. The read file succeeded, which is what we would expect. We close it, and we come out here. Now, in theory, we now have our quote-unquote bitmap memory. Of course, it's not really bitmap, but we could take a look at that memory if we wanted to, right? We can see what's in there, and what we would expect to see is the contents of the file, right? Because that's what we did. We told it to load it off the disk. So here's that address. I'm going to paste that address in here. There we go. And hey, lo and behold, there it is. There's our file. Looks exactly like it looks. So there you go. So that all worked fine. Then we're going to go ahead and free it. Go in here, the virtual free gets rid of it, which is exactly what we wanted. You can see it vapes the release the memory back to the OS, so we can't read it anymore. Exactly what we wanted. So that's all good, and we are pretty much done. That is file I/O. Very exciting. Now again, just to be clear on things, this is only for debugging. You would not want to virtual alloc every individual file like that, because virtual alloc is for large allocations. I think its minimum allocation size is 64K, maybe something like that. It allocates in 4K pages, but I think you can't allocate less than 64 of them, because basically the granularity of it is that. So you're using up that much of the virtual address space. Although you may not care. It's a long story, but point being, you don't want to be doing lots of small virtual allocs. So the only reason we're doing this is because we know that this is only for our debugging purposes. You wouldn't be doing that normally. And if you cared too much, you could do this. You could call heap alloc if you actually cared about it, because that will use the actual OS heap, which is designed for more small allocations like that. But we don't care about that, so we're just going to stick to using virtual alloc for now. So that's it. The only thing we need to do now is basically clone this function for writing. It's pretty straightforward. Basically, we don't need to do any of the allocation stuff anymore, so that simplifies our life quite a bit, nor do we need to get the size for things. All we really need to do is just open the file, write to it, and close it. So basically all we're going to do here is change what we're passing. We're going to do generic write. We're going to say that we don't have any file sharing, and we're going to do a create always, basically. Well, actually, you know what? I got to go look and make sure what the actual flags are for saying we always want to overwrite everything. Let's double check. All right. So create file. Basically, going to take the share mode is 0, right? Other processor from opening at all. That's what we wanted. So we're changing our share mode to 0. We're asking for generic write privileges. We don't need to read from it, so we can just say generic write. And then we've got create always. Let's see. Yeah, so I think we're good. If the specified file exists, the function overwrites the file, which is what we want. If it doesn't exist, a new file is created. So I think that's exactly what we want, because we want to overwrite old files.
I can just write to this file. This is read. You can just do file dot write. Yep. I guess then you could read from it after. Quite straightforward. Yep. This is some test. Edify file write. Right, and then I can also contents. Destination. Underscore equals. Need it right now. Why is it empty? Okay, it read 0. Why did it read? Is it async? Writes to a file descriptor, retries when interrupted by a signal, number of bytes written. Note that successful write runs are fewer than count bytes. Count written. Okay, so the write's fine. It's the read. Yeah, this did write to it. All the script returns a number of bytes that were read, which can be less than buffer length if 0 bytes were read. That means end of file. Wait, file flags. Shows that this open call creates the file, otherwise causes no. If I change that to close a block. That's weird. Oh, sorry. Destination. Line. That's weird. I'm not sure why that doesn't work. File dot read. Let me check. File. Read. Hang on, because okay, I think I need to reset the file handle after write. If I remember correctly, yeah, maybe. I think so. File. It is here. File dot seek. Seek error. No, that didn't work either. File dot get position. Would have been nice if the debugger worked. I think my debugger doesn't work currently. Oh, sorry. Think. Yeah, this doesn't expect. Okay, so it's currently at the end. So if I need to reset. Is there a way to reset? Seg file reset seek position. I'm bashing my head against the wall. That's funny. Seek by, seek from end, set end position. How do I... Repositions right, read write file offset relative to the current offset. What's the difference between that and seek to? Relative to the beginning. Okay, so the seek position is correct now. Still doesn't read stuff. It's weird.
So that should be it. That's all we really need. That's all we really need. So then when we come in here, we're just going to write the memory to it. So we're basically going to do the equivalent of write file, where basically what we do is we pass the memory size there, and the memory, that should be it, like that, something like that. I don't actually know what you pass to write file. Let's take a look. Write file. Doop. There we go. So write file, we pass the file handle, which we did. We pass the buffer, which we did. We pass the number of bytes to write, which we did. Then we need the bytes written, which is the equivalent here, bytes written. And then we've got the overlap parameters. So there we go, basically the same. We are going to basically do none of that. I guess we could log it if we wanted to when we do our logging. And that is it, really. There's not a lot to it. Basically, same stuff here. We're going to assume false failure, and then we're going to set our result parameter to whether the bytes written equals the size that we were trying to write, right, like that. So that's it, really. And you'll notice the way I've structured these, I tend to like to make a result variable, set it to failure at the outset, which I try to make be the 0 value as much as possible. So the default failure is 0 there. I try to do the operations, and when I get all the way onto the inside, I will then set that result to whether or not the thing succeeded, and then let that fall out. That tends to be the way that I write these functions. I find it's pretty clean and makes it easy to verify that everything went okay. So that's our write entire file. Nothing really special there. It's just the inverse of the read. Basically, you know, the opening is the same, and then just instead of calling the read, we just call a write. That's it. Nothing else to it. And of course, we don't need to do any allocations there, so it's a simpler function. So out in here, we could do that now. We could say basically, you know, we don't call this bitmap memory because it ain't a bitmap. So we're basically going to read the entire file. Then if we're here, we'll do platform write entire file. And basically what we'll do is we'll write out a test file here. I'll just say w handmade test.out, like that. And whoop, almond milk fail. There we go. Always got to put it out here a little further. I think that's the right thing to do. Okay, so basically all we're doing here is I'm just going to read the file in, and then I'm going to write out another file that's basically a test file. We'll put that in the data directory just to test it. Let's see. It does not take one argument. You're very right, sir. It does not. Oh, good point. See, this is the thing, people. You always gotta write the usage code, or you're gonna miss stuff. You always gotta have the usage code. Never develop an API without the usage code. So basically, what happened here is I forgot one crucial thing, which is when we actually have these. Where was that? There it is. When we actually have these, when we read the entire file, we need to know how big it was as well. So we actually need a debug read file result. We actually need to return the data, like the contents of the file, but we also need the content size, right? We need both of those things, and we don't have them right now. So basically what we need to do is we need to return this from that read entire file function. Does that make sense? So that was good catch there. Whew. Always write the usage code. You gotta have that usage code. Otherwise you go ship that thing to someone and then you realize that no one can actually use it in practice. It's so good. The usage code saves you so much time. Always, always, always develop the usage code. Develop the usage code if you can. All right, so anyway, here's our actual result. We're gonna initialize that there. And then what we'll do here is when we come through, assuming that the file was read successfully, then we're going to have, and we're going to actually have a void star, well, no, I guess we just have result star contents. So everywhere we were using result before, we actually have result star dot contents is the thing, like this, like that, and like this. There we go, looking good. And then all we want to do here is basically assuming that we actually, if everything succeeded, we're going to set that content size equal to the file size, like that. Let's take a look here. So now we have to actually do this. Debug read file result. File. So we're going to read that in. We've got file.contents. We're assuming that's going to be true. There we go. Then we're going to go ahead and write that out. File.contents size, file.contents, like that. And then we're going to free that memory. There we go. Yeah. So that's...
Actually, that's a better idea. If I have the file, can I just... Full mode. Da-da-da. Interesting. Locks until all pending file contents and metadata modifications. Okay, there's only two.
That's it. I think that's pretty good there. Let's take a look at what happens. Now, and you'll notice, so here's one of those things. If this would have been part of our system, remember I was saying for debugging purposes, it's nice to set that base of virtual alloc. Well, that's exactly what would have been nice here, because our memory window would have been showing the right location already. But since virtual alloc's going to return different things every time, for when we don't specify the base address, it wouldn't. So that's the kind of thing that I was saying for our regular game code. It's nice to have that, when you can get it. Anyway, so here's our file. Let's take a look at the contents to make sure they're correct. There they are. Now we're going to write to this file, so let's step in there. Let's see if we can open that file. Now we should on the drive actually start to see it show up. So if I go in here to the data directory, we should see it. There it is. You notice it has 0 size because it has not actually finished the write to it yet. We'll do the write, and I believe it'll still show 0 size. Yeah. So basically the way that NTFS typically reports these things is it'll say 0 size till it actually closes the handle. So you'll notice the bytes, the free bytes went down by the amount we wrote, so you can actually tell that it did the write, but it stays at 0. Then when we close that handle, we now should see it go to the size. There it is, and off we go. So that's it for that. Off we go. We come in here, we free the memory, and we end. And now, if it worked properly, we should see as well the fact that that file is the same file. So if I go ahead and open it now, right, there it is. And that's what we wanted. All right. So that's about it. There isn't a lot else to it. I don't think we actually need to save this test code anymore because the problem is this path is hard-coded here, right? And we don't really want a hard-coded path in this thing. That was just for testing purposes. So unless we were actually going to start doing it, I guess we could do, you know what we could do? We could just do that. Because the data directory is our startup directory anyway. So
Okay, I think that was actually quite easy to do. Probably the first thing so far in the last 2 weeks. It was easier than the original. I guess this does work. Or not sure. Wait to reset the file. Oh. Anyway, but it does read because I did check. AI test. That does work. I mean, I think I don't even need this for now. I could remove it, write it back later. Because yeah. This was super easy, comparatively. Like what? 30 lines of code? Yeah, less than 30. That's pretty good. Okay, I'm gonna call it a day there. That was pretty easy. Which is good, I'm not complaining, because the last month, quite rough. Yeah, I do get a lot of questions if I'm just streaming Casey stuff. I've thought of that myself. It is kind of, I mean, it's bothered me from the beginning, but the other alternative would be to just watch it on my free time and then just build this. It's a lot more tedious. I find it easier to just do both at the same time. But what I will do is I might try to do more coding. Just try to get the idea of what he's doing and see if I can build it myself. Compile switches. Actually, go back. Might just watch this one thing.
So I like having that just so it kind of sticks out a little bit. Basically what I was talking about here, before we go to the Q&A, what I was talking about is when you write to a critical file, so let's say you've got the unlocks on the user's machine, like what stuff they've unlocked in the game. You typically don't just want to overwrite the old file, and the reason for that is your overwrite could fail and only partially overwrite the file, leaving them with a corrupted save file. So what you want to do instead usually is write to a different file and either have a rolling buffer scheme. So basically you have like an A and a B file, and you write to the B file, then you write to the A file, then you write to the B file on alternating runs of the game, and you load whatever one is most recent. Or you write to a secondary temp file, delete the old file, and then rename the file into place, so that at least you know that the rename would have to fail, but you're not going to run out of space on the drive and fail or stuff like that. So we want to, when we actually do the stuff that writes to the save game file, we're going to want to do something much more protected than this. I hate when games don't do safe ways of saving stuff and then lose your save game or something like that. I hate that. So we're gonna make sure we don't do that. So anyway, I think that's everything for file I/O that we wanted to do. I don't think there's anything else. So next week we should be in good shape to just go through, clean things up. Basically, our clocking values need to be cleaned up, and then look at some to-dos. Keyboard input should be piped through. So we're basically, because we already get the keyboard input, we don't pipe it through our input system. So basically next week, just cleaning up everything that we hadn't actually just finished, and then we should be good to go. We are basically at a place where we've got all the underlying stuff for the game to actually start to exist, which is pretty darn cool. So with that, let's go to the Q&A and see if anyone has questions about what was covered. Please make sure that your question has C. Muratori in it.
Okay, perfect. I think I might be able to skip this one. Maybe not. I'll watch it because my debugger doesn't work at the moment since I updated Zig. My hope is at some point don't have to watch the videos after all the platform stuff is done. I hope. Alright, I think that's it for today. Thank you for hanging out. And I shall see you back here tomorrow.